I'm presenting the final project for the Evolutionary Algorithms course, a genetic programming-based classifier for adult income prediction. Our core goal is to use the GP model to analyze the classic adult dataset and predict if an individual's annual income exceeds $50,000. Next, I'll cover problem background, method design, experimental results, and key conclusions step by step. We use a modified adult dataset with over 14 demographic and occupational features like age, education level, work class totaling around 48,000 samples. The task is clear. Predict if an individual's income exceeds $50,000. Two key challenges. Class imbalance, with roughly 75% of samples in the low-income group, and mixed feature types, including categorical ones like gender and race, and numerical ones like age and weekly working hours. Our evaluation metric is accuracy, with model performance verified via Kaggle's public and private leaderboards. This problem, we've designed a solution with three core pillars. First is advanced feature engineering, deriving new features through domain knowledge to make raw data more predictive. Second is an expanded GP operation set, introducing more nonlinear operations and protection functions to enable the model to capture complex relationships. Third is a diversified ensemble strategy, training multiple GP models with different configurations and using weighted voting to enhance prediction stability. These three parts work together to form the core framework of our entire solution. Feature engineering forms the foundation of our solution. First, we handle missing values. Categorical features are filled with unknown, and numerical features with the median to avoid data bias. Then we focus on deriving domain-specific features. For example, dividing age into groups and labeling elderly or young, calculating total capital gains and whether there is capital inflow, categorizing working hours and marking full-time status, and based on years of education, labeling higher education. For categorical features, instead of traditional one-hot encoding, we chose target encoding, using the income mean corresponding to each category for encoding, which retains more predictive information. Finally, all features are standardized to ensure stable operation of the GP model. After these processes, the number of features expands from the original 14 to 24, significantly enhancing the predictive power of the data. The core of the GP model is the operation set. We've designed a rich array of unary and binary operations to boost the model's expressive power. There are 6 unary operations: negation, absolute value, protected square root, sigmoid function, ReLU function, and step function. These operations can perform nonlinear transformations on individual features. For example, sigmoid can map values to the 0 to 1 range, making threshold judgment easier. There are 4 binary operations: addition, subtraction, multiplication, and division. The division is protected. When the denominator is close to 0, it directly returns 0 to avoid calculation errors. Additionally, we've introduced random constants selected randomly from -3, -2, -1, 0.5, 0.5, 1, 2, 3 to give the model more numerical flexibility. The combination of these operations enables the GP tree to express extremely complex logical relationships. The evolutionary process of GP mainly consists of 4 steps. The first step is tree construction, randomly generating trees of different depths. As the depth increases, there is a greater tendency to generate leaf nodes, that is, constants or variables, to avoid overly complex tree structures. The second step is mutation, for which we've designed 3 methods. Subtree mutation, swapping random subtrees, node replacement, replacing leaf nodes, and constant mutation, modifying numerical constants in the tree. The third step is crossover, exchanging random subtrees of 2 parent trees to combine their advantages. The fourth step is the selection strategy. We use elitism, retaining the top 3 best models in each evolution. At the same time, we use tournament selection, choosing the best from 5 random models as parents. This not only ensures the retention of excellent individuals, but also explores new model structures, balancing exploitation and exploration. I trained 5 GP models with different configurations. Each model varies in population size, number of evolutionary generations, and maximum tree depth. For example, the fast model has a small population and shallow depth, resulting in high training efficiency. The deep model has a large population and deep depth with strong expressive power. As shown in the table, the validation accuracy of individual models ranges from 0.8123 to 0.8194, with the enhanced model performing the best at 0.8194. For ensembling, we assign weights based on each model's validation accuracy. The higher the accuracy, the greater the weight. Final predictions are obtained through weighted voting, allowing better models to play a more significant role. The experimental results are promising. First, looking at individual model performance. Validation accuracy ranges from 0.8123 to 0.8194, with an average accuracy of 0.8154, and the best enhanced model reaching 0.819 for the predicted distribution of the ensemble on the test set is reasonable. 7,709 samples are predicted to have income is less than or equal to $50,000, and 2,060 samples are predicted to have income greater than $50,000, which aligns with the true data distribution. Training efficiency is also good. The entire ensemble model took only 36 minutes to train, which is within an acceptable range. The key achievement is, through ensemble diversity, my model achieved strong robustness on imbalanced data, with stable and reliable prediction results. Finally, to summarize, first, combining advanced feature engineering with a GP ensemble strategy effectively solves the income prediction problem for the adult dataset. Second, domain-specific derived features and target encoding are key to performance improvement. Third, the expanded GP operation set, especially the protection functions, enables the model to capture complex nonlinear relationships. Fourth, model diversity is crucial. Ensembling multiple GP models is more stable than a single model and effectively reduces overfitting. Fifth, the solution achieves a good balance between performance, interpretability, and computational costs, making it practically applicable. That's all for my presentation on the entire project. Thank you all for listening. If you have any questions, suggestions, or topics you'd like to discuss in depth, please feel free to raise them. Let's exchange ideas and learn from each other.